Hello everyone, welcome to day 5 of our journey to becoming a data scientist. And today we'll learn about hypothesis testing. In hypothesis testing, we make inferences about a population based on sample data. To better understand this, let's use a real-world analogy. A criminal trial. So in a criminal trial, a defendant is either considered to be innocent or guilty. This can be expressed as two hypotheses. The null hypothesis, which is denoted by H0 and is called null hypothesis, represents the default assumption, which states that there is no change or difference in the population. In the trial, the null hypothesis would be that the defendant is innocent, reflecting the original assumption about the person before any charges. Whereas the alternate hypothesis, denoted by H1, which is called the alternate hypothesis, on the other hand, is the claim that opposes the null hypothesis. In the trial, this would be that the defendant is guilty. Now, at the end of the trial, if the jury finds the defendant guilty, it means that they reject the null hypothesis in favor of the alternate hypothesis. However, if the jury acquits the defendant, it means that there wasn't enough evidence to support the alternative hypothesis. Keep in mind that an acquittal doesn't necessarily prove innocence. It just indicates there isn't enough evidence to reject the null hypothesis. Similarly, in hypothesis testing, we never accept the null hypothesis. We only either reject it or fail to reject it based on the evidence. Okay, now let's try to understand the hypothesis testing with an example. Let's consider that we are trying to determine that if the average monthly demand for ice creams per store in the summer will be different from the historical average of around 400 units. Now, due to which is anticipated due to a change in weather patterns. So here, how will form the null hypothesis and the alternate hypothesis? So for the null hypothesis, denoted by H0, the average demand for the ice creams per store per month during the summer remains the same at 400 units. So mathematically, it should be given as the mean should be equal to 400 units. This represents the assumption that the status quo holds and there is no significant change in demand. Whereas the alternate hypothesis will be the average demand for ice creams per store per month during summer is different from 400 units. And mathematically, it should be written like this. Now, this challenges the status quo and suggests that the demand has changed, possibly due to unexpected increase in the heat intensity. In hypothesis testing, we test whether there is sufficient evidence to reject the null hypothesis in favor of the alternate hypothesis. If there is enough data to suggest that the demand has significantly shifted from 400 units, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis, implying that there is no strong evidence for a change in the demand. Okay, now let's see with an example. So suppose you have a friend called Tom whose average score in a game, he claims that he has 50. Now, why will you believe Tom with just his words? So you decide to play 5 games with him. And then in the first trial of 5 games, he scored 20. So it's very unlikely for you to believe him. Now, if the score had been not 20 and then 45, it will be more likely for you to believe, yes, indeed, the actual score can be 50. So why is it like less likely for you to believe this, but more likely for you to believe this? Let's understand with the help of the graph here. So if Tom claims that he scored 50, that means the population mean for his game should be 50. Now, if he scored a 20 when he played a game for you, with you, it should be somewhere around here, and we denote it by x bar. Now, if you define a range which is called the critical value, and it could be on both sides. So if this 20, it falls under or above this critical value point, which is denoted by C here, we say that we fail to reject the null hypothesis. Whereas if you increase the critical value point, for example, let's say this is the critical value point, and it falls below the lower limit, we say that we rejected the null hypothesis. So that means Tom doesn't likely to have a mean score of 50. Now this critical point can be in the both side of the test. This is called the upper critical limit. And the one in this side is called the lower critical point limit. Now, as you can see here, we have considered the critical region on both the sides. But is it always the case? It's not, because the critical regions depend on the state of the null hypothesis. Now, what I mean by is that in here, during our null hypothesis was that mu equal to 50, whereas our alternate hypothesis was mu is not equal to 50. So here you can see if the null hypothesis contains only the not equal to sign, it suggests that the test is two-tailed. So that means we'll consider the critical region in both the upper and the lower part. But and this also indicates that the population parameter could be either less or greater. So Tom could have a score less than 50 and also above 50, in which we'll say that Tom was underestimating himself. Now, in two-tailed tests, the rejection region lie on both sides of the normal distribution. These regions capture the extreme values that are significantly different from the population mean. Now, for example, for this test, we can take this example that the score can be either lower or higher than the average, than the claimed average score. Now, if the sign for the alternate hypothesis have a lesser than sign, then it is called a lower tail test, and it is one directional. So what I mean by is that the rejection region, so if we plot the graph, the rejection region is only on the left side of the distribution, indicating that if you are testing whether the population parameter is significantly less than the hypothesized value. For example, if we test the average commute time is less than 35 minutes or not. The next type of one-tail test is the upper tail test, where the alternate hypothesis have a sign of greater than. And it is called the upper tail test. So the critical region, that is the rejection region, it falls on the right side of the normal distribution, indicating that if you are testing whether the population parameter is significantly greater than the hypothesized value. Example, if the average commute time is more than 35 minutes or not. So in summary, the rejection regions for a two-tail tests lies on both sides, and you can find a non-equal to sign in the alternate hypothesis. For one directional or lower tail test, rejection region is only on the left side, and you can identify it by looking at the null alternate hypothesis when we find that there is a lesser than sign. And the third, which is the upper tail test, the rejection region will be falling on the right side of the curve, and you can see if it's a upper tail test by seeing the greater than sign in the alternate hypothesis. Okay, Now, coming to the problem that whether to accept or reject the null hypothesis, we uses a lot of method, but then let's first see the most commonly used method, which is the critical value method. So the critical value method is a widely used approach in hypothesis testing to decide whether to reject the null hypothesis. And here's how to process works even given the example of the ice cream cell that we have seen below. Now, as the owner of multiple ice cream stores, you want to determine whether the average demand for ice creams per store during summer has changed from the historical average of 400 units per month. Based on the new data, you have the following. Now, let's say this summer, based on the sample of 25 units, it shows that the mean sell was 420 units. So now let's form our hypothesis, which gives that the null hypothesis, it returns its status quo, that is the historical average of 400, and we consider that no, there is some change and it affected the alternate, the historical average of 400, and we consider that no, there is some change and it affected the alternative hypothesis that the mean does not remain equal to our historical average. And let's say the population standard deviation is 90. Now let's walk through the critical value method. So the first step in here is to calculate the standard error, which means how much the sample mean is expected to vary from the population mean. So how is it calculated? So the standard error is given by the population standard deviation by root over of number of samples, which is 90 by root over of 25. It gives 90 by 5, which is equal to 18. Now let's set up a significance level. The significance level, which is actually denoted by alpha, represents the probability of rejecting the null hypothesis, which is actually true. So very commonly used significance level are 0.05, which is like 5%, 0.01, which is 1%, and 0.1, which is the 10%. And in this case, let's assume alpha equal to 0.5. Now, how to find the critical value? Now, since you are conducting a two-tailed test, because if you see our null hypothesis only has a non-equal to sign, you need to divide the significance level into two, because if you remember, we have the critical value on both the sides of the curve, since it is a two-tailed test. So if we divide alpha by 2, we get, so this is 0.05 by 2, we get 0.025. Using the cumulative probability corresponding to alpha by 2 equal to 0.025, you can find the z-score that we talked about in our day 2 lecture. So z-score, which is denoted by zc value. And for from a normal distribution table or calculator, you can do it. Now for alpha equal to 0.05, in a two-tailed test, c is approximately 1.96. And in this example, the z-score was within the critical value range, so the null hypothesis was not rejected. Now, this is it for today, and tomorrow we'll see another method which is called the p-value method, which is the more commonly used method, and also we'll see how the z-score can be transformed into t-score, and also like two sample mean test, A/B testing, and others. So please keep following the channel and please keep supporting, and thank you for watching, and I hope that you learned something new from this. Thank you so much. See you next day. Bye bye.